My dear students, continuation of Module 3. Here is Module 3.2. We've just finished with Module 3.1. Module 3.2 is methods of obtaining rate constant and order of reaction. Remember I said that the rate law in Module 3.1 law must be obtained experimentally. So we're going to look at the method we can use to obtain this rate constant and order of reaction. And once we're able to obtain the rate constant and order of reaction, then we can obtain the rate law. We're going to look at methods of obtaining rate constant and order of reaction. We'll be using simple rate equations determined from initial rate methods. 3. Simple rate equations determined from differential rate methods. 4. Simple rate equations determined from integrated rate methods. And then we look at half-life of a reaction and conclude. So methods of obtaining rate constant and order of reaction. The first one we're going to look at is simple rate equations determined from initial rate method. The order of reaction N and rate constant K can be found by determining changes in initial rates with different initial conditions of reactant experimentally. So what that means is that if we have some reactants, let's say reactant A, B, and C, we can keep reactant A and B constant and vary the concentration of C. Whatever happens to the initial rate of the reaction will be as a result of that particular concentration we have varied. Then we'll do another experiment, hold B and C constant and vary the concentration of A. Just like that, so that we'll be able to now record the initial rate and then use that to calculate. So we're going to use an example. A chemical reaction has a stoichiometry A plus 2B plus C giving out D plus E. The effect of varying reactant concentrations on initial rate is summarized below. Look at it, the table. We have experiments 1, 2, 3, 4. Then we have the initial concentrations. You can see the concentrations we have now added subscript 0. That is to tell you that it is the initial concentration at time equal to 0 when the reaction has not started. So for A, we have 0.1, 0.3, 0.1, 0.1. For B, we have 0.2, 0.2, 0.4, 0.4. For C, we have 0.3, 0.3, 0.3, and then 0.6. So we can use this data to find order, rate constant, and of course, the rate law for the reaction. Now, before we go to the next slide, let's carefully look at this because we're going to make use of this table in the next slide. If you look at experiment 1, we have 0.1 for A, 0.2 for B, 0.3 for C. Now if you look at experiment, and the initial rate is 0.05. Now look at experiment 2. You see that it is only the initial concentration of A that is changed from 0.1 to 0.3. Right? Now that of B is still 0.2, 0.2. So nothing changed. That of C is still 0.3, 0.3. But the initial rate has changed from 0.05 to 0.15. So it means that this change in initial rate here was as a result of the change in concentration of A. Because this order B and C are kept constant. So that is how we now have to visualize, look at this table critically and find experiments where the concentrations are the same for 2 reactants and change for only 1 reactant. Let's look at 3 and 4 again. Experiment 3 and experiment 4. For experiment 3, A is 0.1 and 0.1 for experiment 4, so no change. Concentration of B is 0.4 and 0.4 for experiment 4, no change. But C changed from 0.3 and became 0.6 for experiment 4. And the initial rate did not change. You see, so while this C changed, initial rate did not change. So we're going to use this to solve, this example. Now then, from experiment 1 and 2, like I said, we see that the initial concentration of B and C are constant. So it's only A that changed. That of A and B are constant looking at experiment 3 and 4. And then when we look at experiments 1 and 3, so you see, that tells you what is happening, the ones that are constant. So let the rate law be written as, look at the rate is equal to K into A to power small a, B to power small b, and C to power small b. So this is the rate equation we are trying to solve now. Once we get values for K and get values for the small a, b, and c, we'll be able to get our rate law. So dividing experiment 2 by experiment 1, we'll have, look at this, experiment 2 is 0.15, 0.3 for A, 0.2 for B, and 0.3 for C. Divide by 0.05 and all that. So if we now divide 0.15 divided by 0.05 will give us 3. And if you look at this, 0.2 over 0.2 is the same, 0.3 over 0.3 is the same. So this will cancel out. We'll be left with 0.3 to power A divided by 0.1 to power A, which is also 3 to power A. So when we solve that using our laws of indices, log A is equal to A log 3. So log 3 equal to A log 3, A will be log 3 over log 3, which is equal to 1. So the value of our order of reaction with respect to A is 1. So following the same method and using experiment 1 and 3 and 3 and 4, the values of B and C are found to be 2 and 0 respectively. So I will need you to pause this video, go back to the table, look at experiments 1 and 3 and also 3 and 4, and solve the same thing we did and see whether you will get 2 and 0 respectively. So when we now replace that into our equation, we are now going to have rate is equal to K, A to power 1, B to power 2, and C to power 0. Now what is remaining is K. Since we know the rate in the table, we know their concentrations, we can use any of the experiment. Whether you use experiment 1, experiment 2, experiment 3, or experiment 4 to solve, you will get the same value. So we're using experiment 1 here. The initial rate is 0.05. The concentration for A is 0.1, for B is 0.2, and for C is 0.3. Remember, we'll have values of small a as 1, small b as 2, and C as 0. So we'll substitute, make K the subject, and divide, we'll have 1.25. So this gives us the rate constant. So our rate law will now be rate is equal to 1.25 into concentration of A to power 1, concentration of B to power 2, and concentration of C to power C. What this means is that we can use this to model. Assuming the concentration changes to 0.80 for A, 0.90 for B, and 0.70 for C, we can plug back and then estimate the initial rate of reaction. Now, simple rate equations coming from differential rate method. We have looked at initial rate methods. Now we want to look at differential rate methods. Now for this, we need to do a differential, that is differentiate the A over the T, which is equal to Ka to power n. Of course, n is our order of reaction. To determine the rate of reaction, experiments are performed to determine the concentration of A at various time intervals. Then the data obtained can then be analyzed to determine values of n and k. We have two methods. One is rate concentration graph. For zero order, rate is equal to K0. For first order, rate is equal to K1A. And for second order, rate is equal to K2 to power 2. So we have made this before. And the second method is to plot a log rate, log concentration graph. Now, but the major problem with these differential rate method is that it will require an initial plot of concentration against time, and then of course that plot will not give a straight line. So we'll take points and draw tangents at that particular point on the curve, and that gives a lot of errors and is also very tedious to carry out this kind of analysis. So we usually do not employ these differential rate methods. We're just mentioning it for us to know that we can also use differential rate methods to determine the rate constant and other reactions. Simple rate equations determined from integrated rate methods. Now for integrated rate method, we just integrate our equations for zero order, first order, and second order reactions. And then we obtain straight line equations. So when we test any data concerning those straight line equations, it becomes easy. Once it gives us a straight line, then we know that that reaction is following that particular order of reaction. So the hypothetical reaction is X to product. Remember, our rate of reaction is minus dx over dt, minus because X is reactant, equal to K because it is zero. If it is zero order reaction, then the concentration of X to raise to power 0 is 1. So that disappears and we're left with only K0 here. So we cross multiply, dx will be equal to minus K0 dt, and then we integrate. Once we integrate, we have X is equal to minus K0t plus constant. For us to get this constant, we go to our boundary conditions, that is our initial condition. When t is equal to 0, x is equal to x0. Therefore, x0 will become our constant. So we have equation 3, x is equal to minus k0t plus x0. So a plot of x against t will give us a slope of minus k0. And straight line if the reaction is of zero order reaction. So any data that is given, we subject that data to this plot. If it gives us a straight line, then we can calculate the rate constant. And of course, the intercept of that straight line will give us the initial concentration x0. And by so doing, we're able to get the rate constant and order of the reaction. Now for first order reaction, instead of x raised to power 0, x will now be power 1. And anything to power 1 is itself. So we have minus the x over the t is equal to k1 x to power 1. Of course, the negative sign is there because of our reactant. So we'll cross multiply again and integrate. We'll have ln x equal to k1 plus x. And there's minus here, so we'll see our minus. Minus ln x equal to k1 plus x. Then remember, this is law of integration. If you're integrating 1 over x, you'll get ln x. Now we'll go back to the initial boundary conditions for us to be able to get this constant. At the start of the reaction, when t is equal to 0, x will be equal to k0, that's the initial concentration of x. We substitute, and when we substitute, our constant will be equal to minus ln x0. So we'll now solve, and we'll get ln x is equal to minus k1 plus ln x0. This time again, we'll reduce this to a straight line graph. So a graph of ln x against t will be a straight line of gradient k, and the intercept, that is the constant, will be ln x0. Of course, we can also convert ln to log, and that gives us equation 5. If we remember that ln x is equal to 2.303 log x. So we can move from equation 4 to equation 5. And in this case, if we plot log s against t, we'll have a straight line whose slope or gradient will be equal to minus k1 over 2.303. And the intercept will be equal to log x0, where we can calculate x0. Now for second order reaction, determine x to product. We'll do the same thing, except that here we'll now have minus the x over the t will be equal to k2 x to power 2, because we're talking about second order reaction. So we'll cross multiply, collect like terms, minus the x over x squared will be equal to k2 dt. And we integrate. If we integrate, we'll have 1 over x equal to minus K2T plus constant. We'll repeat the same thing again to our boundary conditions. T is equal to 0, X will be equal to X0. That's initial concentration. Then we'll substitute these values in equation 6 and we'll have equation 7. 1 over X is equal to minus K to T plus 1 over X0. So we'll plot a graph of 1 over X against T. If it gives a straight line, the slope will get K2, the slope, and the intercept of 1 over X0. So what we're saying is any data you are given, you can subject the data to these 0 order, first order, and second order straight line equations. And anyone that gives a straight line means that that reaction is following that particular order of reaction. We can get the rate equation. Now, half-life. Now, this half-life is defined as the time it takes half of the initial concentration to react. So, if the initial concentration is 100 moles, if it takes 50 minutes or 60 minutes for 50 moles to react, 50 is half of 100. So, if it takes that time for it to react, then automatically means that the half-life is 60 minutes. So, for zero order reaction, when T is T half, X will be equal to X0 over half. So we substitute to our straight line equation. Instead of X, we now have X0 over 2 equal to minus K0. Instead of T, we have T half plus X0. And we'll simplify. We'll have that T half is equal to X0 over 2K0. So what is this shows that T half depends on X0. And you see that as X0 increases, T half also increases from this equation 8. Now, we'll go to first order reaction. We'll do the same thing. Substitute into our ln X is equal to minus K1T plus ln X0. So now it becomes ln X0 over 2 is equal to minus K1T half plus ln X0. We now simplify. And when we simplify, the X0 will cancel out. It will remain 2. So we have ln 2 is equal to minus K1 T half. So T half will be equal to ln 2 over K1. And ln 2, if you check your calculator, is 0.693. That's equation 9. So this equation shows that the half-life of first order reactions does not depend on initial concentration. Look at equation 9. There is no initial concentration here. So whether your initial concentration increases or decreases, nothing will happen to the half-life. And one of the categories of reactions that follow this half-life is radioactive decay processes. That's why if the half-life of uranium is 1,000 years, for example, whether uranium is 25 grams or 1,000 grams, it will take the same number of years for half of that to disintegrate. Then we'll go to second order reaction. We do the same thing. Go to the second order reaction equation, straight line equation, and then we substitute. Instead of 1 over X, we now have 1 over X0 over 2. So becomes 2 over X0 is equal to K2 over 1 over X0. So automatically we will have, when we substitute, we will have T half is equal to 1 over K2 X0. Again, this equation is telling us that the half-life of second order reactions is also dependent on initial concentration. But in this case, there is inverse proportionality, unlike the zero order where you have direct proportionality. Yeah, thank you very much. We'll be able to look at methods of obtaining rate constants and order of reaction using the simple rate equations determined from initial rate methods, determined from differential rate methods, and also determined from the integrated rate method. And we also looked at the half-life for the zero, first, and second order reactions. Thank you very much, and I hope to see you in module 3.3.